Hello and welcome back. So far in this course, we have looked at a lot of algorithms for reducing the dimensionality, let's say using the Johnson's-Lindenstrass lemma. We have looked at computing approximate nearest neighbors using locality sensitive hashing. And we have also seen how to do PCA or matrix completion type algorithms efficiently by which require computing the singular value decomposition, and we saw how to do this efficiently using randomized SVD, where you get approximate top k singular vectors in a very fast and efficient way. So in spirit of the same spirit of doing computations for large scale data sets or matrices and things like that, we will continue our discussion today for a slightly different topic. So this time we want to look at clustering as a topic. So what I want to do here is first talk about what the problem of clustering is. Many of you might already know this. We'll give a very high level recap, quick recap, and also talk about existing algorithms that you may know already for clustering, specifically the K-means algorithm for clustering, point out some problems with that, and then that will lead us to a new type of clustering, which is a very popular and efficient way to do clustering, but will an algorithm that kind of takes a lot of time and space complexity, especially when you are working with large scale data sets. So then we will talk about how to make this efficient algorithm, which we will discuss, well, efficient in terms of the outputs that it produces, but not computationally efficient. But then we will discuss how to make it computationally efficient. So that's the overall plan for this week, and we will begin slowly. First talk about basic clustering, then go to this new algorithm, and then later make it efficient. So today's discussion is going to be broader, not necessarily going to deal with scale yet. We will talk about general problem of clustering, and then talk a bit about this. I will introduce this new algorithm that we might be interested in. Okay, so what is the problem of clustering? Well, one of the most important problems in machine learning is clustering, which falls under the category of unsupervised learning, by which we mean that there is no supervision provided along with the data set. That is, we just have a bunch of data points and we are asked to learn something from it meaningfully. So you can think of this as the input to this problem as a bunch of data points x1, x2 till xn, where each of this data point might be in some high dimensional space, some feature space, and we want to take this data set and produce an output. Let me call it z1, z2 till zn, where each zi belongs to 1 to k. That is, it's a discrete variable which takes values between 1 to k, which just says that zi says which cluster xi went to. So if zi is 5, then that means that xi goes to the 5th cluster. If then every data point which maps to the 5th maps to a value of corresponding zi equals 5 form a cluster. Okay, so for example, you might have a data set like this with a bunch of points like this, maybe like this. It can be all over the place, but this is just an example, and intuitively we see that these points should form one cluster, these points should form one cluster, and these points should form another cluster. In some sense, we are saying points that are close to each other should form a cluster. So one of the ways to think about this is, in this case, if we know that there are 3 clusters, we can imagine that actually there are only 3 points in my data set, but then the remaining points are some noisy version of these 3 points. For example, in this case, the actual 3 points may just be this point, and this point, and then when a data set was generated, instead of having these 3 points, we got some noisy version of these 3 points, which made the, let's say the 100 points that we have in this data set. So if we hypothesize, right, so this is, I mean, we are just given the data set, we are hypothesizing how this data set might have been generated, and one way to think about that would be to say that there are only 3, representative points, or k representative points in general, and then the whole data set is just some noisy version of these k representative points, right. So if you make that assumption about your data set, then our goal would be to find, these k representative data points, because once you found the k representative data points, then it's just a matter of finding which representative every data point is closest to, and then assigning cluster membership based on distances. For example, if I told you that, hey, these are the 3 representative data points, if I did not tell you the clusters a priori, let's say, right, so the clusters were not told to you, the data points were given. The data points are still here. If I gave you the green points and I asked you, hey, tell me what the clusters are, now you can take any specific red point, let's say this red point for instance, and then I can compute the distance of this red point to make that in a different color. Distance of this red point to each of the green points, and then assign this red point to the closest representative, right, so closest green point, in which case this would be this. If I do this now for every data point in my data set, so I'm going to get this as my cluster, this as a cluster, this as another cluster, right. Of course, it's a trivial task of clustering the data set once the representatives are known. But the interesting question is, we are not given the representative, we are just given the data points. How can we get the representative from this? And many of you may be aware of a nice algorithm that kind of tries to do this, which is the KMeans. Well, this is the KMeans problem, and the algorithm is the Lloyd's algorithm, sometimes also called the K-means algorithm, which does the following, right. So we don't know the representatives a priori, so what you do is you start with randomly picking 3 representatives in your data set, and then clustering the data points based on your current guess for these representatives. And once you do the clustering, now the representative that that comes out of this clustering is just the centroids of each of these clusters, right. So and now I ask the question, is every point close to its own representative centroid than any other centroid? Well, if so, then that point is happy. If not, then it breaks our hypothesis that if there are only 3 centroids and then all the points are some noisy versions of this, right. So that means that every point has to be close to its own centroid than any other centroid, right. So the centroid from whose noisy version it is than any other centroid. So if you find a point which is closer to a different centroid than its own centroid, it should actually belong to the other clustering. So we kind of change the cluster label for this data point. Now you get a new clustering, and then you compute the centroids again and you keep going. So this is the K-means algorithm. So so you have the centroid computation step, and then cluster reassignment step. And these 2 steps are done iteratively until convergence. Of course, one can prove that at every round the average distance of every data point to its corresponding centroid reduces as we do this centroid reassignment over time, over iterations, and so you can argue that it's not too hard to argue that this algorithm has to eventually settle down, by which I mean that it has to eventually reach a clustering where every point is closer to its own centroid than any other centroid. Now, at that point, we would say that the algorithm is converged, and that would be the clustering. Of course, this is an excellent algorithm. It works really well in practice for several data sets. For example, data sets like these where our hypothesis is actually true. which is to say that, you know, there are these representative points, and then all the points are some, you know, noisy version of this representative points that we have. So when that hypothesis is true with respect to our data set, this is a great algorithm, right? So of course you can initialize this well using some techniques, etc., which I am not going to discuss here. For those who have not seen K-means before, and those who are interested, you know, can look up videos. I mean, there are several resources. You know, even the online BS course on machine learning techniques covers this in detail. Today, our focus is not quite the K-means algorithm itself. I just had to discuss this to set some context as to what people might have as a prerequisite before watching this video. So this is something that I'm going to assume as a prerequisite, this algorithm that we kind of know. So one of the properties of the K-means algorithm is the following, right? So perhaps the most important property of clusters emerging from K-means, right? So is that clusters are in Voronoi or convex regions. What do I mean by that? I simply mean that, you know, you can divide your entire input space into K parts using intersection of hyperspaces, half spaces. So what do I mean by that? So for example, you know, if I have two-dimensional data, maybe I'll use a different color for this. Let's say I have two-dimensional data like this, and I have a lot of points. Let's say we are still in the k equals 3 case. I might have points like this. Then, you know, what this means is that, let's say I run K-means, and then, you know, it gave me these points in one cluster, these in one, and these in one, which means that, you know, it would have computed the centroid of each of these bunch of data points and observed that, you know, every point is happy with its own cluster. It need not, I mean, there is no need for a point to jump to a different cluster because it's closer to its own centroid than anything else. Now, if we ask the question, well, where are the set of all points which belong to cluster 1? Let's say this is cluster 1, this is 2, and cluster 3. Now, if I ask where are the set of points that all belong to cluster 1, now that would be in the region which, I mean, that's just precisely the set of points which are closer to the centroid of the first cluster than centroid of the second or the third, which, if you work it out, is going to be, you know, to the left of the perpendicular bisector of the line joining cluster centroid 1 and 2, and at the same time is also, maybe I'll make this dotted, so that's a, assume that's a line. Okay, so also to the left of the perpendicular bisector of the line joining centroid 1 and centroid 3, right? So because, you know, to the left, I mean in this direction and in this direction, right? So which means that the set of all points that belong to cluster 1 will be somewhere here because those are the set of points which are closer to centroid 1 than both centroid 2 and 3, right? So those are precisely the points. So that is region belonging to cluster 1. Now similarly, if we do the analysis for cluster 2, we are going to get another centroid like this, sorry, another perpendicular bisector like this, and it will be to the left of this. So which means, you know, the points that are closer to 2 than 3 and 1 will be this set of points, and the remaining would just be closer to 3 than 1 and 2. So what has happened is, you can equivalently think that the K-means algorithm is trying to divide our d-dimensional space, in this case it is R2, two-dimensional space, into 3 regions, where each region is an intersection of half spaces. For example, this line, perpendicular bisector, divides the entire space into 2 half spaces. So, one on the left, one on the right, and same with this other perpendicular bisector, right. So, this one, it divides it into 2 spaces, one on the left and one on the right, and now when I intersect these 2 half spaces, I get the LO region, right. So, the left half space of the perpendicular bisector joining 1 and 2 and 1 and 3, that intersection is the LO, right. So, and so on and so forth for green and blue regions as well. So, these are called as Voronoi regions. So, these are convex regions. So, a quick recap of what a convex region or a convex set is. So, it just means that if I take any 2 points, right. So, a set is convex. If I take any 2 points in the set, let us say x and y, then if I draw the line segment joining x and y, the entire line segment is within this set. So, the Voronoi regions, right. So, it looks like this, right. So, the Voronoi regions are convex sets, because if I take any 2 points in this region, the line segment joining those 2 points will be in the same region. I can take any 2 points, right. So, the line segment will be in the same. So, basically the yellow region is a convex region, the blue region is a convex region, the green region is also a convex region. Now, because of the way our K-means algorithm is designed, we can argue that the clusters that we end up will be in Voronoi regions, right. So, if they are not in Voronoi regions, then that means that there is some point which is not happy, right. So, so there is one point which is closer to a different centroid than its own centroid, which means that contradicts the fact that the algorithm has converged, right. So, and we have gotten the centroids after convergence, which means that if you really took the centroids after the algorithm converged, then the whole region can be divided into k Voronoi regions or convex sets, and that is a property of the K-means algorithm. Now, that's a fine. So, that's something that comes naturally out of the way we have designed the algorithm itself, and that is okay as long as our hypothesis is true, right. So, why is it okay? Because I mean, our hypothesis itself, if you remember, was to say that there are these 3 representative points, and every point is is kind of something around this representative point, right. So, it is a noisy version of this representative point, which means that it is okay to have Voronoi regions as clusters, because then you will really let me not draw the lines, but just the perpendicular bisectors, you can have Voronoi regions that separate these clusters, right. So, that is a natural way to do the clustering for the hypothesis that we have, that there are only 3 representative points, and the rest of the points are some, think of this as a Gaussian blob around this centroid. Then these Voronoi region based clusterings work really well. But in reality, this may or may not be the case. If this hypothesis is true, then our clustering is good. What we get out of it is good. Naturally, if this hypothesis breaks, then the clustering that we get, well, I mean, the algorithm is not assuming anything about the hypothesis. The algorithm is going to run for any data set that we give it, right. So, but if the hypothesis is not true, then the clusterings that we will get are not necessarily intuitive clusterings that we would expect. Here is an example, right. So, and again, this is an example that you may have seen, example where K-means would fail in what sense, right. So, the K-means algorithm is doing its job, right. So, but it's going to, when we say it fails to produce, and now here is the tricky word, right. So, intuitive clusters. So, for example, let's still work with 2-dimensional data. So, that's perhaps easy for us. And let's say we have points like this. This is sometimes called as the two moons data set. It need not be as structured as I am drawing it. It can be some noisy version of what I am drawing as well. But let's say something of this sort. So we have points like this, let's say, and then some noisy versions of this. So if this is the data set that we have, then one might ask, what first question is, what is an intuitive way to cluster this data set? The second question is, what would the K-means algorithm do? So even before that, the 0th question, so to say, is how many clusters do we think are there in this data set? Now, so there have been cases where I've asked people this question, and most of the times I get the answer that I think is intuitive. But there have been cases where people have given me alternate answers as well. So intuitive is a very tricky word in unsupervised learning. It's always a tricky thing to define what is the ground truth. But I hope what I mean by intuitive is also intuitive to you. So at least to me, it looks like there are two clusters in this data set. The one, the top half moon, and the second is the bottom half moon. So those are the intuitive clusters that I would expect my algorithm to recover, right? So I want this to be one cluster region, and I want this to be another cluster region, right? So this is the intuitive clustering that I am able to visualize in this data set. Now, clearly, K-means is not going to produce these clustering. I say clearly because of the discussion that we just had about what kind of clusters K-means would produce. We know that K-means has to produce convex or Voronoi region based clusters. Now, there is no, if there are only two clusters, K equals 2, then Voronoi region is just, a line that divides my data set into two parts, right? So my region, R2 in this case, into two parts, right? So each half space is one cluster region. Of course, there is no line that can divide, the dark blue from the light blue here. So if I actually ran K-means on this, I might get perhaps, I don't know, so perhaps something like this, right? So meaning when I draw this line, it means that what I exactly mean is these points belong to one cluster, these points belong to another cluster, right? So if you're able to, if you want to look at just the clusters themselves in different colors, so it's going to look like something like this. This is there, and then followed by these points, and now the remaining guys these will belong to one cluster, right? So as you can see, the line itself is this. This perhaps is not the most intuitive way we want to cluster this, right? So this is one example. Of course, now the reason is because the clustering that we want an algorithm to recover fall in non-convex regions, right? So these regions that I am talking about are non-convex because my clustering region looks like this, right? So there is a bend in between, right? So which means that if I take 2 points in my region, which I think of clustering region, then if I draw the line segment joining these 2 points, so there are points part of the line segment which I don't consider as belonging to my cluster, right? So that's the problem, and that's why this is not a convex region, the clustering that we want, and so K-means will not recover it, right? So and so we are calling it K-means fails, simply because K-means is designed to produce convex sets or Voronoi regions, whereas now here is a data set where that does not happen. So, and now it's not too hard to come up with other data sets which have this property. Another simple example, just to show you one more example, would be to have a data set like this, which is the something like a concentric circles kind of a data set. You might have a data set like this with two concentric circles. And now again, intuitively, I might want the inner concentric circle to be one cluster and the outer concentric circle to be another cluster. So, which means that if you think of cluster regions itself, maybe this region belongs to one cluster, everything else belongs to another cluster, right? So, everything else belongs to another cluster, and that clearly is the outer region. The inner region is a convex region, but clearly the outer region is not convex, because if I consider maybe these 2 points, then the line joining them contains points which are not part of that cluster, right? So, it goes through the blue region, so that's clearly not a convex region. Now, the question is, what can we do about this? Well, there are several ways to fix this. I mean, there are several clustering algorithms, that are extensions of K-means that kind of fix this. What I'm going to propose and talk about today is one specific way, a popular way to fix this, which is called, which is called as a graph based clustering, and specifically this is the method that we will look at, is what is called as a spectral clustering method. Again, this word spectral clustering has multiple algorithms associated with that name, and we are going to see one such algorithm, right? So, and then I'll make a statement about, or make a comment about what are other possible ways to, what are other possible algorithms which carry the same name,